Hey folks, I'm Demotro. Obviously I like clocks. There's a bunch of them here, like that one that just fell from the wind. But the clocks aren't the only clock-like cycle in our lives that I like analyzing. Like, for example, weekdays, which I actually now have in a clock-like form. This was sent to me by my combo Lord Stick at the private mailbox. And the weekday cycle is something that we're used to in our life, going from a Sunday to Monday to Tuesday to etc. And we take for granted some hidden fun mathematical patterns in there. Today I was thinking about some mod 7 patterns using what's called modular arithmetic that lets me find cool patterns that I can turn into facts about weekdays for you folks. And I found something that I find interesting. It relates to the weekday cycle, as well as to a type of number called perfect powers. A perfect power being a number that can be written in the form a to the power of b, where a is some whole number that is, theoretically we could call it 0, but let's just say a is a positive whole number, and b has to be at least 2 as another positive whole number larger than 1. So there are many perfect powers we could think of. For example, 2 squared is 4, 3 squared is 9, 2 cubed is 8. You got 5 squared is 25. You got a lot of perfect powers. But what if we tried to go forward a certain amount of a perfect power, amount of days, and we wanted to land on a particular weekday based on the weekday we started on? So, like if we went forward 1,000 days, all that would matter is the remainder when 1,000 is divided by 7, as far as how many weekdays we actually ended up ticking forward. And we can call that the value it's congruent to in mod 7. We're going to make a little chart for mod 7, which technically is a deep mathematical concept that we can think of as basically being the remainder that a whole number would have if divided by 7. Technically, it's infinite classes that numbers can fall into, and we're looking at the simplest member of these congruence classes in mod 7, which are the remainders, in a way, of 0, 1, 2, 3, 4, 5, or 6. Those would be how many weekdays we ended up actually moving if we go a bunch of days forward on a calendar. So, for example, if I go forward 8 days, we're just going to call it 1 weekday that would tick forward, And we'll call Sunday our 0 day. We'll say that Sunday, just to have a neutral standpoint, but we could have picked any day as our 0 day. Let's say Sunday equals 0. Now that's going to mean that since we're ticking forward, Monday is what we'll call day 1, Tuesday is day 2, and etc. And let's say that I want to go forward a perfect power amount of hours, but I want to end up, after starting on my Sunday, on a Wednesday. Now, it sounds like a simple question. There's all sorts of perfect powers, and there's only 7... Whoa, there's a cat way up there. Whoa. Hey, Dandelion, what you doing all the way up there on the fence, mister? Come here, Dandelion. Oh, he'll come down and join us in a bit, probably. Now, there's only 7 options for what it could be. And so that's going to seem like before long we should be hitting some sort of perfect power that would land us on any of the following weekdays, like a Wednesday I wanted to target. And when I said Sunday is 0 and we're aiming for Wednesday, we can think of that as whatever day you're starting on. We're trying to end up 3 weekdays after it. Oh, different cat alert. Here's Sassafras. Here's the stray one who got adopted not that long ago. Hey, Sass. Oh, they love coming into the classroom and helping. So here we have Okay, get this back on track. Here, won't let the cats distract me. We have 7 possible weekdays we could... Oh my god, okay. I said I wouldn't let the cat distract me, but he's up in the tree. These cats do the funniest stuff. What are you doing in the tree, dude? Alright, so now we're done with cats. Back to math. If we have 7 options for where we could land and all sorts of perfect powers, it might surprise you that what I found when I was fiddling around with this today is that the smallest perfect power that would land you 3 days in terms of weekdays from when you started, that would land you if we started on Sunday on a Wednesday, is 3,125. That's a pretty big number for what we might expect. It's the 72nd perfect power. There are more than 70 perfect, that's beginning with 1. Some people, don't count 1 or start from 0 or whatever. Starting from 1, this is the 72nd perfect power. There's more than 70 smaller perfect powers, none of which, if you add that many days, end up 3 weekdays forward. And when I was thinking through why, I realized that the explanation, not only of this little fact, but why this is true, would be useful to make a bonus video about here. I say bonus video because this is technically my bonus channel despite having more subscribers. We have, in fact, done some other episodes that explain the idea of modular arithmetic a little more in depth on my main combo class channel. So if you want to see a slightly more in-depth logic of some modular arithmetic patterns in other mods apart from mod 7, as opposed to just trusting me on some of this, well, there's some links in the description. But with that said, I think many of you will be able to follow this anyway if you think of these as the remainders numbers could have if divided by 7. Now what we're going to do, wipe all these perfect powers away, and make a little chart in mod 7 of our possible values that a whole number could end up what we call congruent to. 0, 1, 2, 3, 4, 5, or 6. And we can think of that as like, before we talk about perfect powers, if I just added a given amount of weekdays, then we're going to either end up on the same weekday, 0 weekdays of change, or 1 through 6 weekdays further than when we started. Now, what if we put on n squared here? These are the start of the perfect powers, and although there are so many square numbers, an infinite amount, in mod 7, we get some shortcuts. We can actually just square the values from 0 through 6, find their result in mod 7, and know that those are the possibilities for any square number in this mod. Because if I tried to do the same thing with 7, I would end up with the result from 0, 8 would give me the result from 1, 9 would give me the result from 2, and so on. Now, n squared for 0 here, and for 1, and for 2 don't overflow at all. Those are numbers in the mod. N squared looks like what we'd expect. But for 3 squared's 9, and that in mod 7, like we noted, is 2. So if I go forward 3 squared days, I end up 2 weekdays forward. Now, if I go forward 4 squared, that's 16, which is 2 more than the latest multiple of 7. 5 squared, 25, is 4 more than the latest multiple of 7. And 6 squared, which is 36, is 1 more. Now, we're going to come back to the fact someday that, as we noted when I showed the base 10 versions of how this affects last digits of numbers, modular arithmetic patterns, here in mod 7, we notice a similar thing that some people commented on. Apart from 0 giving 0, the rest are symmetrical. 142241, 142241. Same both ways. So that's pretty neat. Now we're going to go into why that's the case more in some future episodes. But for today, our first note when we're thinking about how many weekdays we go forward in mod 7 is that no square number sends me forward 3 weekdays. In fact, there's none that sends me forward 5 weekdays or 6 weekdays either. What about cubes? Well, for cubes, I could cube the original numbers, but I can go even quicker by multiplying the result from my n squared box by n, because this is the simplified version of n times n. So to get n times n times n, just toss another n in the multiplication. That times another 0 is still 0. That times another 1 is 1. 4 times 2 would be 8, but in mod 7 that's 1, which, like I noted, we could also get just by cubing that first result and then mod 7ing it. 2 times 3 is 6. 2 times 4 is back to the 1 thing because of mod 7. 4 times 5 is 20, which in mod 7 is 6. And 1 times 6 is also 6 in mod 7. Here we don't have a symmetry. Here we have something a little different. We have like a 2 trios. 1 6 6. Well, a little different. We get 1 1 6. 1 6 6. All we get is 1s and 6s. Now, what's interesting about this is that if you add a cube number of days to any starting day, you will always end up either on the same weekday you started on, 1 weekday forward from where you started, or 1 weekday back from where you started, because 6 is sort of like a -1 in this mod. It's 1 before 7. So we still don't have any 3s, and we still don't have any 5s. This tells me that no square number and no cube number added as an amount of days sends me either 3 days forward in terms of weekdays or 5 days forward. And so to get 3 days forward, we're going to need a number that's not a square or a cube. And that instantly can eliminate 4th powers, 6th powers, 8th powers, 9th powers, 10th powers, because anything with an even power is some type of square number as well. Anything with a 3-even power is some sort of cube number as well. So we in fact can deduce that no number, and we're referring to whole numbers here, to an even power will send me forward either 3 or 5 days, and neither will a number to a 3-even power. This is even more limited in what it has. This is missing the 6s. This is also missing 2s and 4s and 5s. But altogether, neither of them have a 3 or a 5. And since 4th powers are really a square of a square, we can note that it's got to be the 5th power where we end up. We could also take this chain further to come a little closer to that conclusion. Now, when I said it has to be the 5th power, that doesn't have to be the case, because perhaps 5th powers don't work, or perhaps 5th powers, it requires a bigger 5th power, like 6 to the 5th power or something, which would mean maybe there's a smaller 7th power or 11th power or something that does the trick. Does turn out to be a 5th power that'll come in handy for our smallest possibility. Many of you may have spotted that already, that this is a 5th power. In fact, this is 5 to the 5th power. Is the smallest perfect power that sends me forward 3 weekdays. Now, 4th powers here, if I multiply again the last result by n itself, 0 times 0, 1 times 1, 1 times 2, 6 times 3 is 18, but in mod 7 that's 4. And here we have 1 times 4 is 4. 6 times 5 is 30, which in mod 7 gives me 2. And 6 times 6 is 36, which is 1 in mod 7. And hey, look, we're back to symmetrical. It's different. 1 4 2 2 4 1, 1 2 4 4 2 1. But okay, the cat's back in the tree. I know I said there's a different cat. There's Sage in the tree this time. Yeah, I have 3 cats. What are you doing in the tree, man? There's the other one. Look at him peeking over the fence. Okay, I keep saying I'm not going to get distracted by the cats, but they're so cool. So, maybe they'll come help on this side of the camera. Getting back to the math. Ooh, you are so agile. Now, getting back to the math. We're filming this one on my own. Remember, a lot of these bonus videos on this channel are one take because I don't have time to edit them while I'm working on editing my full combo class episodes. So, a little chaotic, but we still have more to learn. So stay tuned, even if you're not a cat lover. If we got these as our fourth powers, and then we went forward to the fifth powers, we can now play the same game, and real quick, I'll write them out without describing as much. I'm multiplying the last one by n again as a shortcut. 12 mod 7 would be 5, and 4 times 4, 16 mod 7 is 2, and then 2 times 5, 10 mod 7 is 3, and 1 times 6 is 6. And what do you know? Fifth powers got me to all the possible weekdays. There's a way to send a fifth power day 1 forward, a fifth power day that goes 2 forward, 3 forward, and etc. Now, if I go further, something interesting does happen, where if I multiply these back again by the last one, I get 3, 4, 5, 6. We get 0, 1, 2 times 4 is 8, sends me 1. 5 times 3, 15, sends me 1. 2 times 4 is 8, sends me 1. 3 times 5 is 15, sends me 1. 3 sends me 1. And we get a strange thing. Look at that. 0 and all ones. We will see that come up again in the future as we investigate more modular arithmetic. Because n to the 7th power sort of fulfills a cycle coming back in a way. And we have 0 times 0 is 0, 1, 1 times 2 is 2, 1 times 3 is 3, 1 times 4 is 4, 1 times 5 is 5, 1 times 6 is 6. And we're back to a beginning of a cycle. And from there, it actually is going to repeat again. And we can see that they're repeating in certain cycles as we multiply forward to further and further powers. Now, what does this mean about the smallest number that goes forward 3 weekdays, like my question was? Well, these are some 3s. Those are some contenders. We got something that ends up 5 more than a multiple of 7 to the 5th power would do that. We also got here 3 to the 7th power will send us there. However, 3 to the 7th power is bigger than 5 to the 5th power. It's not our smallest option. Might look lower on the list if you're just going down this way, but 3 times 3 times 3 times 7 times is bigger than 5 5s multiplied together. Now, that does show us that the smallest type here would be our smallest example. And we may need to, if we want to be thorough, compare it a little further to make sure that, for example, the 11th powers don't have something that would somehow be smaller than that. But it is the smallest, is 5 to the 5th power, which we also could get to with 12 to the 5th power, or any number 5 more than a multiple of 7 to the 5th power. And here, it takes 3,125 ticks, that many hours, or no, days, I think hours because we're talking clock-like, but that many days forward to get to a Wednesday from a Sunday. All the earlier perfect powers can't do it, which we can either deduce by going sideways and seeing how long it takes to hit it, and comparing it to some others. I compared it a little further to make sure. And we can also deduce by the fact that 4th powers, 6th powers, 8th powers, and such are all secretly squares, and must be some rearrangement of these terms. And 3rd powers, 6th powers, 9th powers, and such are all cubes, and must somehow be some form of these terms. And there are many other patterns we could note. Let me know if you find any patterns you want to note about which times on a 12-hour clock or 24-hour clock or 60 minutes or whatever would be harder to get to in this fashion by having to get there from a perfect power spiraling around and adding that much at the end in the mod. So leave a comment if you want to investigate that. I'll do my own fun investigations further into that before long, and make sure that these episode topics will return, because a lot more fun things to say about modular arithmetic. We've also done some division with modular arithmetic and other strange things in some episodes that, like I said, are linked in the description on my main combo class channel. And that's about all for our bonus episode for today. Thank you to all the people supporting on Patreon whose names are in the description, as well as to anybody who signs up for a new membership thing that YouTube is giving me a bonus to start this thing called memberships on here, which I'll explain more in an announcement video when that actually comes out soon. If those don't apply to you, still very glad you're here joining me to watch these fun lessons and cats and nature and stuff. Stay tuned to the main combo class channel, where we'll have some more extra fun topics coming out soon. And on this channel, which is like my personal playground, we will see what happens. I love you all, and I'll catch you again in the next one.